Okay, so in this video we're going to talk about common sets of numbers. This is a pretty important concept in math. So these numbers, there's a lot of different types of numbers in math that show up at various places, various different courses, things like that. So it's important to be able to know the different types of numbers and be able to identify which one's which, things like that. So we're going to talk about them here, talk about some related notation. So for common sets of numbers, the first type of number we'll talk about is a natural number. So the natural numbers here. Okay, so these are important enough so that they have their own special little notation here. And that notation is this sort of beefy looking N. A beefy looking N right here. So it's just a letter N with like these beefy legs, I guess, I don't know, like that. So N for natural numbers. And what are they denoted to be? Or they're denoted like this, but what are they equal to? What are they? So the natural numbers are 1, 2, 3, and then dot, dot, dot. Okay, so again, the dot, dot, dot means continue the pattern. Continue what pattern? The pattern we established here with these first three numbers. So 1, 2, 3. Then if we keep going, we're going to get 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on and so forth. So the natural numbers are basically all the counting numbers. So they're also sometimes called the counting numbers. Because you know, these are the numbers we use to count. So here's 1 marker, 2 markers, and so on and so forth. So we use these numbers to count. So they're also called the counting numbers, but more formally and more often in mathematical literature, like the textbooks and things like that, they're called natural numbers. So next, the whole numbers. Okay, so the whole numbers aren't really important enough to have their own notation, but for the purposes of this video, we'll just call them capital W. Okay? And what are the whole numbers defined to be? Well, pretty much all the natural numbers, but now with 0. So 0, and then all the natural numbers, 1, 2, dot, dot, dot. Okay, so what's the dot, dot, dot mean? It means continue the pattern. Continue what pattern? The pattern I established here. 0, 1, 2, 3, 4, 5, 6, 7, so on and so forth. Okay, so notice this is actually just all the natural numbers. We actually already said it. It's all the natural numbers union with 0. Okay. So be very careful when you talk about it like this. You have to have these curly braces around the 0, okay? Because you can only take the union of sets. So even though it's the natural numbers plus one more number stuck in there, it's actually wrong to say this because you can't union with just a number. You can union with a set whose only element is a single number. Okay, you can do that. Yeah, but be careful. Just when you take a union, you have to take a union of sets. Okay, so this set and this set union together, you get the whole numbers. Okay. I do want to point out that some people do count 0 as a natural number, but it's sort of uncommon to do that. It depends on who you talk to, really. I don't know if anybody really does that nowadays anymore. And it's also, I've seen it more often in computer science than I have in math. But you know, for most mathematical purposes, it's better just to take the natural numbers to be 1, 2, 3, dot, 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 and without 0. Okay, so if you toss in 0, then you'll have all the whole numbers. Okay, but again, the whole numbers aren't really important enough to have their own universally accepted notation. None that I've ever seen anyway, or heard of. But it's more common to just talk about natural numbers. And if you need 0 as well, then we explicitly just throw in 0. So we say the natural numbers with 0. But anyway, you know, it all just depends on who you talk to, what you're reading, things like that. So that's natural numbers, whole numbers. So what do we notice here? Remember we talked about subsets? So we talked about subsets. Remember A is a subset of B if everything in A is also in B, okay? So do we notice a special relationship here? Yeah. Everything in the natural numbers is also in the whole numbers, okay? So what we can say so far is N is a subset of W. Okay? N is a subset of W. Okay? So we'll come back to this also. So what's next? So natural numbers, whole numbers. Now let's talk about the integers. So this is a very important set of numbers here. So the integers, very important set. And it's denoted with the capital beefy Z like this. So Z, short for integer. Actually, Z comes from the German word Zahlen, which means number. So that means number in German, if I remember correctly. So that's where this notation comes from here. Okay, so what are all the integers? Well, there's actually a couple different ways of describing this set. So we could say it like this. Dot, 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 -2, -1, 0, 1, 2, comma, dot, dot, dot. Okay. So we've never seen anything like this before, right, with dots in the beginning and at the end. So what does it mean to have dots in the beginning? Well, let's forget about that. Let's just look here. -2, -1, 0, 1, 2, dot, dot, dot means continue the pattern. Continue what pattern? The pattern I established here. -2, -1, 0, 1, 2. Looks like I'm just increasing by 1 each time. And that's actually what I am doing. So the next number will be 3, 4, 5, 6, 7, 8, 9, and so on and so forth. What if I go back the other way? 2, 1, 0, -1, -2, -3, -4, -5, -6, -7, and so on and so forth. Okay. So the integers, basically, it's all of the natural numbers with 0 and all of the negative natural numbers. Okay. So, or we could say all of the whole numbers with all the negative natural numbers as well. Okay. Now, if you don't like this double ellipses here, you could say it like this also. So that'll be 0, 1, -1, 2, -2, 3, -3, dot, dot, dot. Okay, and again, what does the dot, dot, dot mean? It means continue the pattern. Continue what pattern? The pattern I've established here. 0, 1, -1. No clear pattern emerges yet, but let's keep going. 2, -2, 3, -3. Aha. 1, -1, 2, -2, 3, -3. I'll bet next is 4, -4, 5, -5, 6, -6, and so on and so forth. Okay, so that's another way of describing the set of the integers here. Okay, so these are all these are all integers here, and again, you know, we're just listing all of the same elements, just in a different order. Okay, so if you don't like using 2 of these ellipses, 2 of the dot, dot, dots, you could list it like, or you could say describe the set of integers like this, and you'll only have to use one of them. Okay, so that's another option there. Anyway, what do we notice here? How do the whole numbers relate to the integers? Well, we see here 0, 1, 2, dot, 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 0, 1, 2, dot, 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 plus other stuff. So notice W is actually a subset of Z, right? Because everything in W is also in Z. Okay, everything in here, 0, 1, 2, 3, 4, 5, 6, dot, 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 is also in here. 0, 1, 2, 3, 4, 5, 6, dot, 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 right? So W is actually a subset of Z. Another way of saying that is every whole number is an integer. Okay? So W is a subset of Z. Okay. And again, just W, it's not really universally accepted notation here, or there's no universal standard as far as I know, and as far as I've ever seen or heard. So we don't make this one beefy. Just for the purposes of our video, we'll just use the W. But N and Z, those are universal notations here for natural numbers and integers. Okay? So notice every natural number is a whole number. That's what this says. Every natural number is a whole number, because the natural number is a subset of the whole numbers. So every natural number is a whole number. Every whole number is an integer. Okay. So transitively, really, every natural number is an integer. Okay. So let's continue with this. So natural numbers, whole numbers, integers. What's next? What's next is rational numbers. Okay, so rational numbers, you know, see they have this has the word ratio in it. So these really do involve ratios or proportions or division, fractions, things like that. So rational numbers are also very, very important. So they get their own notation as well, a universal notation, which is a beefy, goofy looking Q thing. So you might see this in textbooks or things like that. So the N, the Z, and the Q, they will show up in textbooks and other types of mathematical literature. So be sure that you're able to identify those. Okay, so with rational numbers, we can't really list them out the same way we listed all these out, but what we can do is describe them using set builder notation. So we could say the set of all rational numbers, that's the set of all P divided by Q, such that P and Q are in Z. Okay, so this so this means element of, so P and Q are elements of Z. So this just means that P and Q are integers, right? So remember, Z represents the integers, and this notation means element of, we talked about in an earlier video. And we also require that q is not 0. Okay, why do we require that? Because you're not allowed to divide by 0 ever. No matter what you're doing in all of math ever, you're never, ever, ever allowed to divide by 0. It's just not allowed. So that's why we just require that q is not 0. Okay, so nothing really special there. Okay, so when we listed all these out, it's easy to see what's a natural number, what's a whole number, what's an integer. Well, what's a rational number? Okay, let's see some examples of those. So if we come over here, basically any fraction you can write down where the top and the bottom are both integers and the bottom's not 0, that's a rational number, okay? So 1, 2, 3 over 4, 5, 6. Okay, so these aren't guaranteed to be in lowest form, but anyway, 1, 2, 3 over 4, 5, 6, so that's a rational number, right? It's so this is our p over q. They're both integers, right? 1, 2, 3 is an integer, 4, 5, 6 is an integer, and 4, 5, 6 is not 0. Okay, so that's an example of a rational number. What about negative 52 over 117? Yeah, that's also a rational number. How about 12 over negative 600? Yeah, 12 over negative 600. Okay, so of course that's not reduced, right? Not reduced, but it doesn't matter. Okay, to be a rational number, you don't have to be reduced. You just have to be a ratio of two integers, or expressible as such anyway. So 12 over negative 600, it can be reduced, but still, it's a rational number, because integer on top, integer on bottom, that's not 0. That's it, okay? But also, so to be a rational number, you don't have to be expressed in this form. It only has to be possible to express you in that form. So let's say 1.732 is also a rational number, okay, even though it doesn't really exactly match this form, but we could write this as 1732 divided by 1,000, okay? So 1732 divided by 1,000, that's the same thing as 1.732. Okay, so 1.732 can be expressed in this form like this. Therefore, 1.732 is a rational number, okay? So basically, any decimal like this, so any fraction or any decimal that doesn't repeat infinitely with no pattern, okay? So actually, even if you repeat infinitely, so let's say if we have like 1.732 like that, so remember this notation means the 2 repeats, so it's 1.732 2 dot dot dot, okay? So the 2 just keeps repeating forever. Even things like that, those are also rational numbers, okay, because it is possible to express them as a ratio of two integers, okay? It's kind of weird and kind of tricky and kind of beyond the scope of what we want to talk about, but it is possible, okay? But anyway, so these are all examples of rational numbers. So decimals that terminate a finite number of decimal places, any fraction, any ratio of two integers like that where the bottom is not 0, or any infinitely repeating decimals where you just end up repeating the same thing over and over. Okay, so things like this, or even things like this, let's say 71.862, or even if 2 digits repeat. So that's 71.862626262 dot dot dot. Okay, so even stuff like that, that's also an example of a rational number because it's possible to express this as a ratio of two integers. Okay, again, it's kind of goofy, it's kind of weird, it's kind of tricky to be able to do that. Or it is kind of tricky to actually do that, but the point is it's possible, it can be done. Okay, so again, a rational number is any kind of fraction like this, a ratio of two integers, any kind of decimal like this that terminates after any number of digits here, or any kind of infinitely repeating decimal where you have a part that just repeats over and over again. Okay, so it's important that if it's an infinite number of decimal places, it's important that you have to have the repeating here. Okay, so if you don't have the repeating, and it goes on infinitely, then it's not rational. That's a different type of number we'll talk about soon. Okay, so those are all examples of rational numbers. What else could be a rational number? Well, hey, integer over integer. What if we say something like 12 over 1? Is that rational? Yeah, okay, because it's integer on top, integer on bottom. The bottom is not 0. But what is 12 over 1? It's 12. What kind of number is that? It's a natural number, it's a whole number, it's an integer, okay? What about negative 12 over 1? Well, it's the same thing as negative 12, right? So yeah, that still counts, right? So the point is the bottom here, when you talk about a ratio of two integers, the bottom could be 1 If the bottom is 1, what do you have? You have p divided by 1. P divided by 1 just gives you p. What's p? P is an integer, okay? So basically, what the point I'm trying to make here is that every integer is a rational number. Okay, every integer, it's just a special kind of rational number where the denominator is 1. Okay, so every integer really is a rational number, or in other words, everything in here is also in here. Okay, everything in here is also in here. What does that mean? That means Z is a subset of Q. Okay, so we can come over here, we can say, okay, Z is a subset of Q. Okay. Okay, so natural numbers, whole numbers, integers, rational numbers. Every natural number is a whole number. Every whole number is an integer. Every integer is a rational number. Okay. Okay. But again, the whole numbers aren't really as important, so we don't talk about them as much. So we could just skip that and say every natural number is an integer. Every integer is a rational number, and so on. Okay. So two other types, or really three technically, but two that we want to talk about in detail here. Okay, so rational numbers. The next two types we want to talk about together. So there's rational numbers. Now there's also irrational numbers. Let's talk about real numbers though. So we have irrational numbers and real numbers. Let's talk about real numbers first. So real numbers and irrational numbers. So irrational, that's kind of the counterpart to rational. Okay, so real numbers, they're also extremely important in all of math. So the real numbers, they also get their own notation, and that's kind of this beefy looking R. Okay, so some people like to connect it over here. Doesn't really matter though. I don't really do that, but just a habit, I guess. So anyway, beefy looking R type thing, R of course for real. And it's harder to describe what these are. So basically it's, the real numbers, the set of real numbers, is all of the rational numbers together with the irrational numbers. So what's an irrational number? First of all, they're not really important enough to get their own notation. So just like with the whole numbers, we just gave them one for the video. So let's call these guys I for irrational. So be careful, don't confuse that with integer, you know, I for irrational, but it's Z for integer that comes from the German word Zahlen. Okay, okay, so irrational numbers. This is things like the square root of 2, the square root of 3, the square root of 17, pi. So know this number pi from, you might have talked about that in geometry class. You know, this relates to circles, like the area of a circle is pi times the radius squared, things like that. Okay, so that's what irrational numbers are. Also root 33. Okay, things like that. So basically the square root of anything that's not a perfect square. So like the square root of 9 is 3, right? So that's not irrational. That's actually an integer, which makes it rational also. Okay. It's also a natural number. Okay, so it's actually every type of number we talked about so far: natural, whole number, integer, and rational. So anyway. But like the square root of, so the square root of 9 is 3, so that's not irrational, but the square root of 3 is irrational, okay, for example. So irrational numbers would be something like, if you tried to express them as a decimal, it would be infinitely, it would go out infinitely far, but it wouldn't repeat. Okay, so remember, rational numbers, you could have decimals like 1.732, where the 2 repeats, that's rational. But if you just have like a non-repeating pattern, say like 1.732, 5, 6, 5, 3, 1, 8, 9, 4, 7, 6, ... and this just keeps going on forever without ever repeating. Okay, so if you have infinitely many decimals or infinitely many places after the decimal point and no repetition, there's no repeating anywhere, then that's an irrational number. Okay, and all of these numbers actually have that property: square root of 2, square root of 3, root 17, pi, root 33. They all have that property that they repeat, or sorry, they don't repeat. They have infinitely many decimal points, or sorry, infinitely many places after the decimal point, and they never repeat. Okay, so that's a very important distinction there. If you have the repetition, it's rational. Without the repetition, and if it's still infinite, then it's irrational. Okay, but if it terminates after a finite number of spots, like if we just had this, if it stopped here, even though that's a lot of decimal places, that's still rational. Okay, this is rational because we can express it as a ratio of two integers, right? But again, if we if we keep going on forever and ever without repeating, okay, if you just have infinitely many places after the decimal without repeating, then it's irrational. Okay, so very important distinction there. Okay, so that's what an irrational number is. So the irrational number is the set of all things like, that. So it's really not really a good way to describe the set, but it's harder to describe the irrational numbers and the real numbers. But basically, the real numbers, it's all of the rational numbers. So let's actually keep the colors consistent at least. So all of the real numbers is all of the rational numbers union with the irrational numbers. Okay. Okay, so the real numbers, that's all of the rationals union with the irrationals. Okay. So a real number is really almost any kind of number you can write down or think of. Now there is something more complicated called a complex number, but we don't really want to talk about that too much yet. So it's sometimes, depending on where you are, sometimes it does show up in an intermediate algebra course. Sometimes they hold off until college algebra or pre-calculus or something like that. Anyway, complex number is, it's a little more complicated than a real number. But anyway, I just want to point out that something like this does exist. But we'll talk more about that in a much later video. Okay, so I just want to point out that there are other types of numbers out there, for example, complex numbers. But we don't want to get too crazy, nothing too complicated yet in this video. But anyway, as far as just real numbers go, okay, well, how does this fit in here? So how does the real numbers, how do they fit in here? Okay, well, first of all, how do we get the real numbers? We take all the rational numbers, union them with irrational numbers, okay? So basically, what does that tell us? Well, that tells us the real numbers, it's made up of rationals and irrationals. Okay, so the real numbers actually, if you have a rational number, that is a real number, okay? Because every rational number is a real number. Every irrational number is a real number, okay? So basically, that tells us that the rational numbers, that's a subset of the real numbers, okay? We can actually get that just directly from here, okay? This right here tells us that every rational is a real number. Every irrational is a real number, because we have to union these two to get the real numbers, okay? So anything in here, anything in Q is automatically an R, just from this union here. Anything in I is automatically an R from the union here, okay? So Q is a subset of R, because everything in Q is automatically an R, which is exactly what this tells us here, okay? So Q is a subset of R. Oops, let's maybe make that a little better. Q is a subset of R, okay? Now the irrational numbers don't really fit into this, okay? So the irrational numbers don't fit into the scheme here, but we could also say that the irrational numbers are a subset of R, but really, who cares? The irrational numbers, they're just kind of separate. So the irrational numbers really are separate from everything, okay? But here the point is every natural number is a whole number, but even that, who cares? The whole numbers, they aren't really that important. So when you go into later math classes, after intermediate algebra, things like that, the whole numbers really aren't talked about that much. It's just the natural numbers that are important, the integers that are important, the rational numbers and the real numbers, those are important. The irrationals, not really as much, but we could still talk about them in terms of reals and rationals. But anyway, so if we want to really summarize everything, then every natural number is a whole number. Every whole number is an integer. Every integer is a rational number. Every rational number is a real number. And also, every irrational is a real number. Okay? So those are common sets of numbers and how they all relate to each other. So in the next video, we'll do an example of identifying types of these numbers here. Okay? So that's natural numbers, whole numbers, integers, rational numbers, real numbers, and irrationals. And natural numbers, integers, rationals, and reals, by far the most important types. And they have these notations here that go along with them. So you'll want to make sure that you're able to identify those in case you come across them in a textbook or something. So that's common sets of numbers and an example in the next video.